And the new motivation is that this is really fun part for me to just say it. There's some hard calculation going on out there by many mathematicians and all that, but it's still easy to think about it like this. All right, again, linear transformation, I ask you to look at it as a physical phenomenon that's happening in some position right there. Everybody see it. But if you wanted to measure it, where is it? You want to bring in the coordinate, right? You have to use a reference frame of reference. And where's wind is blowing, then you have to use that reference frame to describe it as a matrix multiplication, not t, right? So that's this pattern here. And how is this? So for example, here's a t, and here's a position, here's a wind vector w, right? Now, if you use a certain basis b, b1, this is described in the matrix M1. Isn't that right? We got that M1. So everybody see what this B1 and this arrow and M1 is? M1 is the matrix of T relative to what? A basis B1. Good? The other guy is looking at the same position, but their frame of reference is different, B2. Isn't that right? And they got their own matrix M2. Right? But how is these two related? Anyone know how they two are related? What is the word? How do you go from M1 to M2? The quick action that you do and you arrive at M2. What is it? Conjugation. If you conjugate M1 with some matrix, transition matrix P, right? Then you will arrive at here. The other guy is also staring at that same position and same phenomenon, but their frame of reference is different, and M3 is there. Their matrix is different. But how they're all these matrices are related? Through conjugation. The word that describes the relationship in mathematics is a similar, right? So if these two matrices are similar to each other, there must be some unknown matrix, invertible matrix P, such that if you conjugate, you reach the other one. If there is this existence, we don't know how to find it, existence right there, if it is so, we call this similar. It is just abstract thinking. In practicality, the finding P is hard calculation. Make sense? That's called similarity, and you understand the motivation of it, right? Because they're all describing same phenomena, even though they all look different. Isn't that right? Yeah. So, for example, okay, that's great. I understand the notion. Then how do I determine? I give you one matrix and I give you another matrix. Is this similar to each other? That means you have to find P, right? Such that you show that I multiply P inverse to the left and P to the right side. I got the second one right there. Therefore, it's a similar, right? So how do we determine that? Think about row equivalence. I give you a matrix, augmented matrix, another augmented matrix. How do you determine whether they have a same solution set? Answer? How do you determine these two augmented matrices have exactly the same solution set? What's that? No, the more specific word I'm looking for. That's called the row equivalence, right? Row equivalence. How do you determine the row equivalence? I have two completely different looking matrices. How do I determine they have the same solution? What's that? Reduced echelon form. If you do reduced echelon form, they're exactly same or not, that tells you whether they have exactly the same solution or not, right? The whole semester is about that and looking at it in a different context, right? Pretty much summarized. Now, new question is that how do we do that? If I have two matrices like square matrices, how do I determine they're similar to each other? What process is it involved in? Okay. Fair question? Yeah. That motivates. Next part. The answer, let me tell you this, answer goes really deep, and you will see the full answer at the end of the second semester of linear algebra. This is for a semester, and you will sign up in the second semester in the fall. All the way towards the end of the semester, you will see that it says advanced linear algebra, intermediate, next level of linear algebra. And the term is that Jordan canonical form. Reduced echelon form, what is the analogous version of a similarity? Jordan canonical form. So if you reach that, if you look at the Jordan canonical form, you see, oh, they're similar to each other. You go to Mathematica, or there are programs there. If you type a Jordan canonical form of this matrix, Jordan canonical form of that matrix, boom, they calculate in a millionth seconds. And then you look at, oh, they're the same. Therefore, they are similar to each other. You can do that. But that process takes long time to understand. However, what we are about to learn is a lot simpler thing, right? That a lot simpler thing, what I mean by that is that matrix we've seen before, 1, 0, 0, negative 1. Do you remember this matrix? Was one other thing that I could go through quickly. Do you agree this is diagonal matrix? Yes. Off the diagonal is a 0. So our goal at hand right now is that see if we can multiply these two things, diagonalize it, turn it into diagonal. If they have the same diagonalized item, if it's one is there, negative one is there, that's equivalent. If I can brought these two matrices the same diagonal form, you have a conclusion they're similar to each other. They're describing the same physical phenomenon, right? But that's not the full answer. Not everything is diagonalizable. That's my quick answer, right? So uh, that leads you to how do you do that? And you have to find what vectors? Eigenvectors. Those eigenvectors. Reflection stays in there going across. The v goes to negative v, and v1 goes to v1, v2 goes to negative v2. They are excellent examples of eigenvector. Something simple is happening to that vector. Going opposite, stay as it is, or just twice the multiplication. They're eigenvectors, right? So you go for eigenvectors. If you can find many eigenvectors, you can diagonalize it. If you find a very small number of eigenvector, you are in trouble. This is not going to work. So then you go to computer and type what? Jordan canonical form. And then it tells you to do that. But we're going to go only up to diagonalizable matrices. Good. All right, I'll see you on Monday.